Good day everyone. Today we're going to be going over volumes and integration, and the volumes we're going to be constructing today will be made through rotations about an axis. Specifically for this lesson we're going to be rotating about the x-axis, and right at the end perhaps we'll try to look at what happens if we rotate about the y-axis and how that affects us. So for this specific short video we're just going to be looking at how we can come up with a formula in terms of integration tactics that we have done so far. So before we start in, I want to give you an idea of what a rotation about an x-axis in a 2D plane looks like. So I'm just gonna draw a little function here, and it's gonna be a straight horizontal line. Say y is equals to k, where k is a constant, a positive constant, and this is going to be our x. So if I rotate this y is equals to k, I'm just going to change the color right now. Roughly speaking, it's going to turn out to be a cylinder, because it's going to go like this, and this is just projecting outside of the screen. So I hope you can picture that into a sort of cylinder like this. And then if it's going to rotate a full 360, it's going to go to the back as well, back into the screen, and then you're going to see the same projection happening like this until we have a full-fledged cylinder with a radius of k and a center of 0 there. Okay, so I think I can call up an app that can help us visualize that. So here it is. So as you can see, this is a 2D presentation. Here we have a straight line, y is equals to k, where k right now looks to just be above 2 and below 3. So if we try to see the rotation, we would just have to change the angle, and there we go. So this is a 360-degree rotation, or 2 pi rotation, and you can see it more clearly like that. We've rotated a straight line, you can see it going like this, you can see it just as the top there, and then we rotated it around here, and it formed a perfect circle with radius k again specified. So this specific line has been rotated around the red axis, so you can imagine the red axis being the x-axis we talked about. I hope this gives you a sort of idea. So we're gonna use this idea of rotations and specifically this cylinder to come up with a formula, because I imagine you as well have worked in the past with cylinders and their volumes, so that should make life a bit easier. Okay, so now let's go back to this. Let's go down a bit, and then we're going to start working with this cylinder. I'm just going to clear this out so that we can start afresh and have something better to work with. I'm going to use the black pen. Okay, so we have a cylinder with us, and I'm just going to draw it here. This is going to be very important. Let's just put it like that. And that's going to be the x-axis, and that's going to be the y-axis. So let's say that the height of this cylinder at any given time, we're just going to call it y of x, because it makes sense that at any particular point in x, the height would be y of x, which is y. So we remember that the volume of a cylinder, if you remember correctly, would be the area, the cross-sectional area here. So we're just going to say area multiplied by its height, and this is very important. So we know that from here to there we can just call it a to b, in terms of these are points of x. So height can just be b minus a. So we're going to come up with a new variable here. We're going to be say change of height. Change of height is b minus a, and that's just going to be b minus a. So it's just going to be this whole section there. And better yet, we can just call this change of height and we say it's going to be called change of x. It might look familiar, therefore our change of x is going to be b minus a. And now our volume is looking like area times change in x. Okay, so now this area, this cross-sectional area, I'm just gonna demarcate it with a bit of color so that you understand which area we are talking about. We're talking about this cross-sectional area which goes throughout here. I'm just gonna say area there. This area, we can find it using our understanding from primary school of the circle. So the area should be pi r squared multiply, and then we have our change in x there to give us the volume again. So pi is a constant, and r we've said that the r is our radius, and then we're going to express the radius at any given time. So this is a cylinder, that means there's constant radius y of x. So pi is going to be equals to no, not pi, I'm sorry, volume is going to be equals to pi y of x all squared multiplied by change in x. Okay, so now we have our change in x there, but we want to limit it, so sort of so that we can have a sort of integral there. So if we say limit as change in x goes to 0, because we want to find the fine summations of our area, saying for very specific change in x here, which is going to be very small, we want it to go towards 0, as we did with integration when we started. We're saying as it goes to 0, we want to see what volume looks like for the same limit. So our change in x goes to 0 is going to become a differential. So we're going to have pi the integral of y of x all squared, and our differential is going to be dx now. So small change in x became dx. And since we want to maintain that we are integrating from a to b, then we're going to change from a to b. I hope that makes some sort of sense. So just like that, if our limit of changing x goes to 0, we are left with the formula that v is equals to pi the integral from actually a to b, sorry about that, a to b y of x squared dx. And just like that, we have a formula for integrating rotation. So this y of x doesn't just work for straight lines as well, you can use it for different functions. We're gonna see in the coming examples we can use even for functions like this, provided that they are continuous and they are two-dimensional. We can use this y of x. We can use any y of x in this function to find the volume. So in the next video I'm going to be covering specific examples, starting from a simple one and maybe trying out a more difficult one to see how we can apply this formula